Welcome back to another lecture on mechanics of machinery. In this video, we will be solving a problem for velocity analysis of slider crank mechanism. So here you are having the crank and connecting rod length is 0.5 and 2 meter. Crank is rotating at 180 rpm in clockwise direction. So when the crank has turned through 45 degree from the inner dead center, you have to determine these 5 parts. So first we will be talking or mainly concentrating on the velocity of piston and angular velocity of connecting rod. Then we have to obtain the velocity of some point E which is coming somewhere in between the connecting rod. And next we have to find the rubbing velocity. About rubbing velocity we will be talking. And last we have to find the position and the linear velocity of the point G which are coming somewhere which it is having the least velocity relative to the crankshaft. So first we will be solving the first two parts 1 and 2. So for that first step is you have to construct the configuration diagram. So for constructing the configuration diagram, I will be marking the point which is representing the location of crankshaft, and this point will be coming on the fixed one, and I am naming it as point O, and I will be taking protractor and marking 45 degree and drawing a line. So for that you have to select a suitable scale. Here I am selecting a scale of 1 centimeter is representing 0.2 meter, so that the 0.5 meter line can be represented by 2.5 centimeter. So at 45 degree, I will be drawing this line. So this line will be drawn according to the scale which is representing the crank. And then I will be marking these dotted lines which are representing the movement of the slider. And this will be the line where the joining between slider and connecting rod is coming. So with this point B as center, I will be taking a distance corresponding to 2 meter. Connecting rod length is 2 meter. So if I am converting into scale, this line will be becoming 10 centimeter if I are drawing. So with the composite to one end at this point B, and I will be marking an arc. So this will be cutting the horizontal line at this point, and this point I will be calling as point B. So now we are having the slider crank mechanism. The configuration diagram is complete, and you can draw this block which is representing the slider. Next we will be naming the different points. So here I already named point O, this is point B, this is point P. About E and G we will be talking later. And here I will be naming the fixed link. This one is the fixed link, and this point on the fixed link is O. Similarly, I can name this point also O because this is also a fixed point, and the point which is coming in a direction perpendicular to the line of action and passing through the point will be touching the ground, and the same point I can name that as O. So O is representing the zero velocity point. So this O is the zero velocity point when you are drawing the velocity diagram. So this is representing the same point because it is coming on the fixed line. So next you will be drawing the velocity diagram. For that it is given that the crank is rotating at 180 rpm in the clockwise direction. So this is rotating at 180 rpm. So now crank is link OB. So you can find a velocity which is velocity of point B with respect to O. And this you are knowing that this is link length OB into omega of OB, which is equal to OB is 0.5 meter and omega OB is given which is 180 rpm, that you will be converting into radians per second, which is 2 pi n by 60. So 2 pi into 180 by 60, and if you are finding this will be equal to 9.42, almost 9.42 meter per second. And this is the magnitude of velocity vector BO, and you are knowing that the direction is perpendicular to link OB. That means this vector VBO can be drawn in a direction that is perpendicular to link length OB. So for constructing the velocity diagram, I will be marking the zero velocity point first. So zero velocity point will be marked here, and this is zero velocity point is O. Next I have obtained the first vector which is VBO, whose magnitude is 9.42 meter per second and direction is perpendicular to OB. So for drawing this one, here also you require a scale, and here I am selecting a scale in such a way that 1 centimeter in my velocity diagram will be representing 1 meter per second. That means if this is 9.42 meter per second, then this should be represented by a line having approximately 9.4 centimeter. So I'll be drawing a line, and that line should be perpendicular to link OB to represent this vector. So this direction I'll be transferring to this diagram, and this will be coming in this way. So I'll be drawing that vector whose length is 9.42. So this is the vector, and this is having the end points. This point I will be calling as B, and this will be the velocity vector VBO whose length is 9.42 centimeter, representing 9.42 meter per second. Here I am talking about the major points only. Points E and G I will be marking later. So configuration diagram we have mainly 3 points: O, B, P and O. So this O is already marked on this velocity diagram. B is also marked in this diagram. So in configuration diagram you will be using capital points, and in velocity diagram you will be using small points. And next you have to mark the point P. So P is the point on the slider, and you are knowing that this slider will always move in this line, along this line of motion. So you can find a velocity vector, that is velocity of point P with respect to O, and this is representing the velocity of slider whose magnitude is unknown. So magnitude you are not knowing, but direction of this vector is known. This direction will be horizontal, because this is moving in this direction. So this direction, that is velocity of P with respect to O, I can transfer onto this direction. So out of this P and O, I am already having the O point here. So I will be transferring this direction of the vector VPO onto this one. So I can draw a horizontal line, and I am not knowing in that line where P is coming. So I will be drawing this line. So some line, horizontal line will be coming, and this will be going in this way. So somewhere in this line the point B is coming, point P is coming. So how you can locate this point P? For that you will be considering the next velocity vector, which is velocity of B with respect to P. So here we are having one link which is PB, that is the connecting rod. So for the connecting rod you can define velocity of point B with respect to P, and this is having some general plane motion. So for the link also you can write the magnitude as link PB into omega PB, where omega PB is the angular velocity of connecting rod, which we have to find in the second part. So this magnitude is unknown, but direction you are knowing that it is perpendicular to link PB. So link PB is there on configuration diagram, and that perpendicular to link PB is to be transferred onto the velocity diagram. So this velocity vector VBP is perpendicular to link PB. PB is coming in this way and perpendicular will be in this way. So you have to transfer this perpendicular line onto this velocity diagram. And at which point you will be making the construction. This perpendicular direction can be transferred to this point or to this point. So which will be you will be making. Since the vector name is VBP, you have to mark point B, and already you are having point B. So I will be making construction at this point. So in a direction perpendicular to link PB, construction line will be made at this point. So you will be drawing the line perpendicular to this point, and that will be intersecting at this point. So this point I will be calling it as P, and now you are having a vector which is coming in this way. So this one I can name it as VPO. Arrowhead is directed towards P, so it will be named as VPO. Next, if I am putting arrowhead here, then this will be known as velocity of B with respect to P. In another way, if I am putting the arrowhead here, then this will be becoming velocity of P with respect to B. Anyway, both are representing the same thing. So in the first part, you have to calculate the velocity of piston. So velocity of piston or velocity of slider. This will be giving you the velocity of slider. So this will be giving you the velocity of slider or velocity of piston. So you will be measuring the velocity diagram. Velocity diagram is having a scale which is 1 centimeter representing 1 meter per second. So whatever be the length that you are obtaining from this one will be giving you the answer. So velocity of piston, if you are observing, the value will be becoming, if you are measuring, you will be getting something around 8.1 meter per second. more accurately, you will be getting this as 8.15 meter per second. So the first part answer for the first part is 8.15 meter per second. Next, you have to find the angular velocity of the connecting rod. So connecting rod is the link PB. So you have obtained the velocity of VBP here. So earlier you are not knowing the magnitude, but directions was known. So based on that I have constructed. Now we are having the velocity vector, this VBP. So from this vector you can measure the distance. So if you are measuring, you will be getting VBPS around 6.8 centimeter in diagram will be getting, and that is equivalent to 6.8 meters per second. And from this you can find omega of link BP or the connecting rod equal to VBP divided by length of connecting rod PB, and this will be equal to 3.4 radians per second you will be getting. This is the answer for the second part. So this is the answer for second part. Now you have obtained the velocity of piston as 8.15 meter per second and the angular velocity of the connecting rod as 3.4 radians per second. Next you will be looking on to the third, fourth and fifth part of the question. So next we will be solving the third part of the question, where you are having a point E which is coming on the connecting rod, and E is at a distance of 1.5 meter from the gudgeon pin. Gudgeon pin or piston pin is coming here, and from that point at 1.5 meter distance this point E is lying. So you have to find the velocity of this point from the velocity diagram. That means you have to mark this corresponding point on this velocity vector. So how you can locate that velocity on this velocity diagram? For that I will be showing an example. So here we are having a link and this is fixed at this point, so it is rotating at an angular velocity omega, and zero velocity point I am naming it as O, and here you are having some point A. So the velocity of point A with respect to O you can represent it by a vector, and I will be calling this vector as velocity of A O, and its magnitude will be OA into omega. If I am considering a point here B, then this will be having velocity, and I will be drawing a vector of this much length only, because if I am calling this vector VBO, then its value will be OB into omega. Since OB is less than OA, the velocity vector length will also be shorter for the VBO. So if I am drawing the velocity diagram, first I will be marking the zero velocity point. Next I will be drawing this vector where this point will be A, and point B will be coming somewhere here based on the length. So this point will be B, and I can mark this vector as VBO, and this will be VAO. So this velocity vector length is depending upon their dimensions on the configuration diagram. So I can have a conclusion that the ratio of the length of velocity vectors VAO with respect to VBO will be same as link length OA to OB. So the same concept I will be using for solving the third part. So here in third part you are having a point E which is coming at 1.5 meter from the point P. So you are having distances PE, capital P on configuration diagram, and capital PB on configuration diagram. Similarly, you can have velocity vectors, velocity of point E with respect to E, as well as velocity of point B with respect to P. So out of this, which are known and unknown, that you have to obtain. So here the PE distance is 1.5 meter. PB distance, the length of connecting rod, which is 2 meter. VEP, this is the unknown quantity, so this we have to find. And VBP, so from the earlier part we have obtained that this is drawn to a scale of 1 centimeter equivalent to 1 meter per second, and this vector is representing 6.8 centimeter. So in the earlier part I have shown that. So this is 6.8 meter per second or 6.8 centimeter. So from this you can solve and find the value of VEP. So if you are solving, so you will be getting the value of VEP as 5.1 meter per second if you are solving. That means the length of velocity vector VEP is 5.1 meter per second, means point E will be coming. This is drawn to a scale of 1 centimeter equal to 1 meter per second. So point E will be coming somewhere here where the length PE, that means this much distance is equivalent to 5.1 centimeter. So you can obtain this point E here, and now here you have to obtain the velocity of point E on the connecting rod, that is coming here. So for finding the absolute velocity, you have to connect that point to the zero velocity point, wherever zero velocity point is O. So you can connect this point to point E. Now from this one you can obtain the velocity. That means this one is giving the velocity vector VEO, which is asked in the third part. So VEO you can measure, and this will be equivalent to 8.5 meter per second. If you are measuring, you will be getting as 8.5 meter per second. This is the answer for the third part, and here itself I will be solving the fifth part also. And in this one, here you are asked to find the position and the linear velocity of some arbitrary point G. It is mentioned that there is some point G which is having the least velocity related to the crankshaft. That means crankshaft is coming here, which is a zero velocity point. So with respect to the crankshaft, which point on this connecting rod is having least velocity? That means you have to, for finding that, you have to draw a line from point O onto the connecting rod. Here connecting rod is PB. So this is PB and equivalent vector is this one PB. So you have to draw a point on from the point O to the line PB such that the distance is shorter, so that this angle is 90 degree. Then you can locate a point G here. So here I will be drawing a line from this point O to this one such that this angle is 90 degree, and then you can call this point as G, and this vector will be giving you the answer for position. You have to evaluate linear velocity of any point G. So you can measure the VGO. This is one part of the fifth category, and that value is 8 meter per second. That means least velocity of any arbitrary point on the connecting rod is 8 meter per second, and its location you have to obtain. So location, again you can use the ratio theorem, which is length PG capital on configuration diagram, PG divided by length PB will be equal to VGP divided by VBP. So here you are having the point, this is actually small g. So here you are having all these values, VGP from vector it is known, VBP is known, PB is known. So you can evaluate PG, and if you are observing that PG will be equal to 0.53 meter, you will be getting. That means this length PG will be, or the point will be lying at a distance of 0.53 meter from the Gaussian pin. So this 0.53 meter from the Gaussian pin is the position, and linear velocity of that point will be 8 meter per second for the minimum velocity for a point that is coming on the connecting rod. So this is the answer for the fifth part. Next we will be seeing how to solve the fourth part of the question, where we have to find the rubbing velocity. Here rubbing velocity is a term which is used for turning pair. So here in slide diagram mechanism, you are having three turning pairs. One is coming here at this point O, another at point B, another at point this P. So for a turning pair, here I am representing a turning pair which is formed by two links. So one pin end of the one link 1 will be getting inserted into the whole end of the link 2, so that they are forming a turning pair. If these two links are having angular velocity omega 1 and omega 2, then the rubbing velocity is defined as the radius of the pin into omega 1 plus or minus omega 2. When this plus sign is coming, if these links are having angular velocities or rotating in the opposite direction, minus sign is coming here if they are having the same direction of rotation. So here I will be finding the angular rubbing velocities of different links at a different turning pair. So first turning pair is this point O. So here you have to find the rubbing velocity at point O, and this will be equal to radius of the pin at O into omega. Here only, if this is connected, I can number this link as 1 the fixed link and 2 as the crank. So here 1 is fixed link, so it is not having any angular velocity, and then remaining this will be the omega 2, that is the angular velocity of the crank, which was given as 180 rpm, and this is equivalent to 18.85 radians per second. So if you are multiplying, this radius of this pin is given here, the pins of diameter of pins are given. So diameter of pin at a crankshaft, which is 50 mm, that is at a point O you are having a pin of radius 25 mm. So this is equivalent to 0.025 meter. And if you are observing this, the velocity you will be getting, the rubbing velocity at this point will be equal to 0.47 meter per second. Next, similar way, I will be finding the rubbing velocity. This rubbing velocity at point P I will be evaluating. So at this point P, this is rotating. The slider is not having any rotation. So it is, that means this point P is coming between slider and connecting rod. Slider is not rotating, so it is not having any angular velocity. Only connecting rod is having rotational motion. So in a similar way, the rubbing velocity at point P, I can write it as radius of pin at P into omega of connecting rod I am naming in as 3. So this will be equal to omega 3. In the second part, we have find the angular velocity of connecting rod. So this will be equal to the diameter of pin at crosshead, or the piston is given as 30 mm. So which is equal to 15 mm radius, or 0.015 into omega 3 is 3.4 radians per second. This we have evaluated. So if you are multiplying this one, you will be getting it as 0.051 meter per second. So last part is you have to find the rubbing velocity at point P, or the where the connecting rod and crank are getting joined. So here both the connecting rod and crank are having angular velocity. The angular velocity of connecting rod is 18.85 meter radians per second, and this is 3.4 radians per second. So next you have to get whether it is omega 1 plus or minus the second. So this is actually omega 1 plus or minus omega 2. So here the radius of pin at B into omega 2, which is crank, omega 3, in between which sign you will be placing. So here if you are observing, the arrow is coming in this way, means crank is rotating in clockwise direction. Here for the point B, this arrow is coming here. That means this is moving in a direction. B is having an angular velocity directed towards this one with respect to point B. That means it is rotating in an anti-clockwise direction. Means here crank is rotating clockwise, this is rotating in anti-clockwise, so directions are opposite. So plus sign will be coming here. So there will be plus sign, and this will be equal to radius of the pin at point B, or the crank is 60 mm. So radius is 0.03 into omega 2 plus omega 3, which is 18.85 plus 3.4. And this you will be getting it as 0.6675 meter per second. This is the rubbing velocity. So we have evaluated the rubbing velocity at all pin locations. These are the values. So we have solved all the 5 parts of the question. Hope you understood this one problem. This will take some time to understand. You have to draw all these vectors, diagrams, and understand. So thanks for watching.